I'm generally against measuring people. We don't say how many papers. How many papers is a really bad question, always. The reason that most of us are in academia is the fact that we love the topics that we work with and we want to work in a personally fulfilling way.
Imperial College has been ranking number 2 in the QS rankings for 2 years.
But I actually don't believe in university rankings. Whether we're rank 1, rank 2, rank 3, I really don't care.
You've been working on some research using FPGA as the computing engine, especially for AI applications, right?
I think it's actually one of the most exciting things that we've been doing recently.
Geoff Rickenton recently talked about the safety of AI. He's quite concerned, like if AI is being developing at this speed.
AI systems are tools. Now that doesn't mean it's not dangerous. There are many dangerous tools out there. My concern is that the profit motive pushes innovation to happen more rapidly than might be safe to happen.
One single most important capabilities for the PhD students to study.
I think the one thing that you really need to develop early on, ideally before you start the PhD, is a natural curiosity. If you don't like the field, definitely don't do a PhD. But if there's one thing that I would take away from my entire career, actually from undergraduate onwards, it's that.
你好，我是芯片工程师老石。今天我访谈的对象是帝国理工学院 George Constantinides 教授。他曾是帝国理工电气与电子系电路与系统研究组的主任，工程学院的副院长，可重构计算与 FPGA 领域的国际知名专家。对于我来说，他还有一个特殊身份，那就是我的博士导师，是那个改变我人生的男人。这是他第2次来我们的频道做客，我把摄影棚搬到了伦敦，我们聊了人工智能和可重构芯片的重要突破和未来发展，他如何看待学术科研，也分享了他为何辞去副院长的职位，从头建立了一个帮助青年科学家发展的新机构，以及他对读博的见解和思考。我仿佛又回到了10几年前读博的时光，每次向他请教，我总是深受启发。视频比较长，但如果你能看完，相信肯定会对你有所帮助。话不多说，接下来就是我和 George Constantinides 教授的对话。
Welcome, George.
Thank
nice
you.
to have you. We're currently in London, as people can every now and then can hear, like in the traffic, people's talking. And I think that's the beauty of Imperial College, isn't it? It's like located in central London, very convenient historical places. Mm-hmm. So you spent your undergraduate, your postgraduate, your PhDs and entire career so far at Imperial College. Yep. So what's so special about Imperial?
Yeah, so I'm an Imperial College lifer. So I guess, for me, Imperial, any workplace really, is only as good or as valuable as the people there. I guess for me, it's about colleagues. I've been fortunate to have some great colleagues at Imperial, continue to do so. Great mentors, I'm sure we'll get on to talk about that in due course. And great PhD students like yourself. And I think, for me, for as long as an organization is continuing to provide an intellectually stimulating environment with great people to work with, why would you leave?
Yeah. That's a very solid, solid reason. So Imperial College has been ranking number 2 in the QS rankings for 2 years. What's your view on that?
Okay, so it might be a controversial view, but I actually don't believe in university rankings. Firstly, they focus on what's measurable easily, and what's measurable easily isn't necessarily what's of most value. Secondly, they try to take what is essentially a really complex question around a vector valued at least metric and scalarize that into a single number. And I think the amount of information that you lose there is more than the amount of information that you gain by looking at these things. I really don't believe in rankings. The other side of the story is, as a result of being one of the highly ranked universities, we get good students. And I definitely believe in having good students. So, I've got to take that advantage. Yes. But beyond that, whether we're rank 1, rank 2, rank 3, I really don't care.
Yeah. Being the top ranked universities, as you said, it will bring talents and
Yes.
students
Yes.
and coming over. It really doesn't really matter if you are. What's the difference between 2 and 3 and 10?
Yes.
Going back to electronic and electric engineering, you spent your undergraduate, postgraduate, and your entire academic research in EEE department.
Yes.
So what's so special about EEE?
So actually, my undergraduate and my PhD were jointly between electrical and electronic engineering and computing. I've always tried to straddle that boundary between electronic engineering and computer science. So I've made electronic engineering my home. I think, again, it goes back to the question of who you get to work with. I've been very fortunate to have Peter Chung as my mentor at the electrical and electronic engineering. The culture in the department is one, I would say, primarily of collaboration, which is very important to me. I really like working with people who want to collaborate and are open to sharing ideas and working together.
That's actually one of my questions, following up questions, right? So in terms of the atmosphere, so the environments of the department or the university, and also in terms of the engineering, which one would you like best or prefer? Is this the solving existing questions or problems, or like creating new things or theories?
I actually don't think that they are separate. They're kind of a dialectical relationship, let's say. I'm by instinct, as an engineer, or at least as a research engineer, I feel like I'm a creative person. So I enjoy creating new things, new ideas. But I think even if you have an existing problem, if you're going to solve that in a new way, that's creating new ideas. So I think I'm all about novelty and working out new ways of doing things, whether those are completely new problems or whether those are new ways of solving existing problems. I think both are creative activities. I think so. Every university and every institution, and it's also true in industry, probably has actually a variety of cultures, right? It's not just a uniculture place. But I think certainly the group of people that I've been lucky enough to work with, that's definitely within our DNA, yeah. And I guess we also, it's not just about kind of collaborative problem solving, it's about being excited about the work, right? I mean, there's nothing for me that's more exciting than working on a technical problem with some new angle or new idea, right? And I think that having that excitement it's tangible in the department.
But which one is the first, right? You find your things excite you the most, or if you're working on the area and then you figure out like you're excited about this stuff.
Well, I think same answer as before, really. It's a kind of dialectical relationship. I feel there's no obvious, it's a bit of chicken and egg, right? Either can happen. I think if you look at the tasks that you're undertaking in a creative and first principles way, then I think very quickly you start asking questions. So you read a paper and the paper says we did X, Y, and Z and we got this result. And so you can reproduce that. But if you're kind of looking at it from a research perspective, then you're actually asking all the time, why did you do X instead of X prime? Why did you do Y? Could you not have done something else? And those kind of questions, even if they're addressing the same problem, lead on to new problems and new answers and so on.
So let's talk about the research you've been working on. So previously, you've been working on something called lossy synthesis. And then during my PhD, we've been collaborating on approximate computing. And then in the AI era, this kind of methodology or concept has been well adopted by many people. Can you take us back to the moment when we first view inaccuracy as a resource rather than a defect in circuit design? So why are you thinking this in the first place?
Yeah, it's a good question. So again, going back to my mentor, Peter Chung, when I started my own PhD, one of the very first meetings I had with him, he said to me, look, we do digital design by using things like VHDL and Verilog at the moment. But in the labs, I use MATLAB. Couldn't we just use MATLAB to do digital design? That was his question. Right? So I went away and thought about that. and really looked at the question of what digital filter implementation in MATLAB would look like and digital filter implementation in modern hardware would look like. And the first thing that was really obvious to me was that they were going to be operating on different data types. And then the moment that you start thinking about the fact that they're operating on different data types, then you start having to think about, well, what's the implication of that when it comes to the quality of result? And so it's really at that moment when I started to think through the implications of that question that I started to think, well, wouldn't it be great if we could actually allocate the resource where it's needed? So in the context of digital filter design, that was at the time we were mainly interested in silicon area as versus signal to noise ratio. If you can allocate hardware resource where it's going to have a limited impact on area, but a significant impact on signal to noise ratio, better to allocate it in that place than in the design where it's going to have a massive impact on the area, but a really small impact on signal to noise ratio. So starting to reason about imprecision as a resource, as you put it, I think is really from then.
So do you think in the AI era, when people doing AI chips, is the approximation or the proximate computing concept still key, like in the future?
I think it's kind of core to everything that happens in machine learning, which is why machine learning is really a huge playground for this kind of activity. It's a different form of approximation, or at least a different form of measuring the quality of approximation. It will depend, and I think as AI evolves, the ways that people will measure approximation change. You know, in a classifier problem, it might be something like the probability of a misclassification, right? Accuracy, essentially, which is a very different idea of quality of numerical behavior to, say, in a high-performance computing application where you're interested in the worst-case error being bounded by a certain amount. So I think, yes, it will continue, and yes, it will be key because it has an impact, huge impact on resource utilization and energy, not so much area these days, but energy is the key resource that everyone is trying to optimize and will be for at least as long as CMOS exists. So I think, yes, it will continue to be the case, but what will be the notion of inaccuracy, what will be the notion of error will evolve over time and has done.
During this trip from word length optimization to approximate computing to nowadays, like in AI chips, people quantize things. Can you come up or think of a few like milestones people using inaccuracy in their digital circuit designs?
We've really talked about probably what I'd say are the three key milestones. There's the kind of early work around signal processing, and then there's the middling work around trying to make use of that in high-performance computing. I've got to say, that never got as developed as I would like. And then there's the kind of explosion of machine learning. I'll tell you an interesting example, right? I was doing some work, some consultancy work for high-performance computing. I was working very hard to convince the company that I was doing the consultancy work for that they would be okay with a 1% change in accuracy as a result of the optimizations I was proposing. They were absolutely clear that that wasn't acceptable, and that the only thing that would be acceptable is if they had exactly the same bit pattern as if they implemented it at the output on an x86 CPU. They changed their mind, by the way, when we could show a 10 times speed improvement, but that was the initial thinking, at least. You will not find that way of thinking in a machine learning world. And that's really the advantage of working nowadays in a machine learning world, is that people are completely open to completely different results because ultimately there's a stochastic element to those results in the first place.
So from the methodology or mindset shift or changes, like HPC is still there, but AI is exploding. But with this trend, the underlying hardware of your research is still FPGA, it's reconfigurable hardware. So that must come for a reason. Can you elaborate a bit more? Why are you so interested in FPGAs or reconfigurable hardware?
Yeah, there's a few different reasons. So if I'm completely honest, going back to my starting point about that research is about getting excited, it's because it's a playground, right? Reconfigurable computing is like being a kid running around in the playground and trying out all these different new toys. So it gives you an environment that you can do that you can try out new ideas. I don't see any other hardware-oriented environment where you can try out those new ideas. I mean, that's kind of my emotional response, right? I'm thinking about it more scientifically. There are really two reasons why you may wish to use an FPGA. They're prototyping for perhaps an ASIC implementation, or they're as the end implementation medium. So if you want to use an FPGA for the end implementation medium, there's good use cases for that, right? Either you've got a very small volume, so it's very specialized, and I work with companies as well as researchers where that's the case. You may also wish to use an FPGA because of super fast time to market. I have this idea, the amount of time required to spin an ASIC is going to be significantly more than to program my FPGA. So those are the kind of two reasons to use it as an end goal. If you're chasing an already established market where the designs are not changing too significantly and it's a big market, then you wouldn't use an FPGA as your end platform. But then if you're trying to innovate in the architecture for your next generation, how are you going to test those innovations? You still need a playground to test in. And so I think that where an FPGA is used in an end application shifts and has shifted over the entire duration that FPGAs have been used for computation, so like since the mid-1990s, right? But whether they are used for prototyping hasn't shifted, right? They will always be used for prototyping. Now, FPGAs themselves have evolved. So when I first became involved with FPGAs, there were multiplexer-based FPGAs, and there were also 4-LUT-based FPGAs, right? Those were the two types of FPGA that were available at the time. And kind of now we have obviously like a much more rich FPGA fabric than existed at those times. But programmability in the hardware level is core to experimenting with hardware.
Yes, absolutely. So my channel, this channel, we talk a lot about the FPGA reconfigurable computing technologies. A lot of people actually get involved in the area because of the videos we've been making. So previously, like you said, so the computing paradigms shifts, like people are using FPGAs for AI workloads, for example, like Microsoft is using it in data centers when AI is first coming out. But recently, when the large language models explode, the benefits of FPGAs is getting lower and lower. And it's kind of many people thinking like FPGA is being defeated by GPUs in terms of computing power. No people is actually using FPGAs for like AI model trainings or like tasks probably. So do you think FPGA still plays a role in the AI era at all?
Well, so again, I think we need to split between in prototyping and in implementation, right? So in prototyping, yes, and they do. I mean, every innovation that a computer architect will make will have gone through FPGA prototyping, right? So there's no doubt about that. If we're asking about the end implementation, again, it depends on the market size. And so I think the real question is not so much, should it be FPGA, should it be GPU, and so on. The question is really, how specialized an architecture are we likely to see in the future? If everything is going to be the same LLM in the future, and everyone's just going to want to run that same model and ask it different things in the future, then no doubt FPGAs are out of the window as a final implementation platform. What you want is an ASIC specialized to that LLM and that LLM only. I think that's unlikely. But I think that an element of streaming in terms of what different architectures might look like, you won't want to pick this architecture for this use and this architecture for this use, that will continue to evolve. I think there's another element which is perhaps more interesting from a scientific perspective as well, which is that when I say, FPGA versus GPU, for example, I'm not actually really often talking about the underlying hardware. I'm talking about all the infrastructure that goes with that hardware and the whole software stack that goes with that hardware. And there's no doubt that the software stack that has been built on top of the GPU is immensely more sophisticated and deeper than the ML stack that's been built on top of the FPGA world. There's a question about how to best leverage that stack in a different architectural platform, whether that's an FPGA or just an improved GPU. And so I think this kind of idea of performance portability is going to play a key role in the future.
Okay, what's the reason GPU got its very mature ecosystem for the very fast, rapidly developed software ecosystem for the past, say, 10 years? Well, FPGA still got its, developments like RTL codings and not really easy to use software. So what's the reason causing this giant gap between those two devices?
Yeah, that's a really hard question to answer. So, I think firstly, FPGAs so you're viewing an FPGA as a computational device. But that's not how all FPGA users are going to view an FPGA. A classical hardware designer doesn't think, oh, look, here's something I can perform computation with. And the history of the FPGA is that it's used for glue logic. Right? It's not used for computation at all, prior to the 1990s. So I think there's a kind of question about who's using it and who the manufacturers and the people who are building on that are using that for and what their expectations are. I think there's a question about the role of open source software and what role open source software can play in this kind of ecosystem and the level of open sourcing that's happened in these two different communities. And then I think there's also just a question of expectation. If you're an ASIC designer and you move to an FPGA set of design tools, you might actually think these are quite user-friendly. If you press compile and something doesn't terminate for 10 hours, that's okay, right? If you're a software user and you type GCC and it doesn't terminate for 10 hours, you're just going to laugh, right? So I think there's a kind of question of expectation there as well. So it's complex because there's commercial aspects combined with expectation aspects, combined with cultural, combined with scientific merits, and they're in a very complicated mix.
It is. You've been working on some research using FPGA as the computing engine, especially for AI applications. For example, using LUT to map neural networks. Can you elaborate a bit more on this kind of hardware native approach compared to directly mapping a random network directly on FPGAs?
Yeah, so I think it's actually one of the most exciting things that we've been doing recently. I still think there's a huge amount of work to do in this space, and I'm super excited to work with people on this. If you look at what a kind of standard design technique is for hardware implementation, we can forget FPGA even, right? Just say a hardware implementation of a network. You start with an abstraction, which if you pick up, deep learning theory books, for example, and read them, you'll see tensor algebra in there. You'll see a lot of numerical linear algebra-based activity and so on. And that's nice because it provides us with a mathematical framework within which to reason. Then, when we want to actually implement a network that's based on that, it's historically been the job of the architecture designers and the IP designers to come up with abstractions which more or less behave like this nice mathematical abstraction that we've been working with, right? So let's say it's a matrix multiply working over real numbers, then it's the job of the IP designer to come up with something that behaves a bit like that. It won't actually be that because nobody works with real numbers, right? But it'll be something like that. So that's the kind of the contractual relationship, let's say, between someone who deals at the IP level and someone who deals at the system software level, someone who deals at the application level, someone who deals at the mathematics level. They kind of hand over that contractual relationship. So my argument is this: those who are involved in the design of the hardware are having to make the hardware terribly inefficient in order to provide that level of abstraction to those dealing at a higher level of abstraction. So instead of thinking about it like that, let's think about how we can expose what the underlying hardware looks like to the mathematical abstractions that we deal with when we're talking about deep learning. Because then if we can optimize over what the hardware actually looks like, rather than an abstraction of what the hardware looks like, then we should be able to do much better in terms of efficiency. So whether that's LUT-based networks, which is what I've been working on for a while, or whether that's other hardware-based ideas that come to play in the implementation of networks, I think that's core. It's exposing what the actual hardware looks like to the training methodologies.
So what's the future of this research will look like, assuming like everything's working on, like is going on well? What's the ultimate target of this research will going to end?
Yeah, so I mean, I think firstly, I don't know. That's why I want to work on it. That's what research is about. But what I would like to be able to say is, come back in 5 years maybe, I'd like to be able to say, look, for this class of applications, the idea that you should work with, linear layers plus these particular activation functions, the classical activation functions and so on, is really old-fashioned. And what we really need to be doing is to be thinking about this in terms of things like Boolean logic. And once we start thinking about it in terms of Boolean logic, you can see that we're going to have like much better latency, much better power, and so on. I don't know what the final abstractions that will settle on are. There are a number of, we can talk about it more, but there's a number of different challenges in determining what that appropriate level of abstraction is. At the moment, I'm interested in just ripping them all apart, right? And just seeing where we land.
Right. Would that be like a revolution of FPGA architecture, probably? Because, like I said, originally FPGA got 4 LUTs and then got 6 LUTs. And then new FPGAs got AI engines built in. Would that be like new paradigms or architecture reform of the FPGA?
Yeah, it's a really interesting question. So my work in this area has not been on improving the FPGA architecture. It's been on exposing the FPGA architecture to the deep learning methods. I have colleagues, for example, Vaughan Betts at the University of Toronto, who's been looking at it the other way around, who's been looking at the question of how do we change the architecture in order to best reflect the abstractions that we're dealing with. I think the future is likely to be a combination of the two. And so by iterating, essentially the reason FPGAs have the components that they have in them today is because they're common components. And so it makes sense to provide them. But how did they get to be common components? It's because people started using them for those things, right? Nobody would put a multiplier in an FPGA if people hadn't started to wanted to do multiplication in an FPGA, right? So I think you need that iterative process to converge in the long term on what future FPGA architectures might look like.
In what field would you expect this type of technology will be adopted or applied? Will it be like edge computing or like small portions of applications as you mentioned, or like a wider or broader usage?
So I can certainly say where I think they would be applied first, because the real advantage of the kind of techniques that I'm working on is where you have very, very low latency requirements. And so I can think of kind of 2 areas where they're likely to be applied immediately, if not already being applied. One is in things like high energy physics, where we've taken some of our benchmarks from. And in the less scientific space, also in computational finance. There's a lot of people who need very, very low latency computation in trading systems. And in those situations, I think, again, that'd be almost immediate adoption of this kind of idea. I think the longer term is likely to be less driven by latency and more driven by energy consumption. And there, I think it's a far more complex picture, what the future will look like, because there's so many different contributors to energy consumption.
So what's your broader view on AI generally? Like we talk about using AIs to software tasks, like people have been using it for coding software stuff. Do you think AI is going to be used for hardware designs at all?
So I think there is already work. It's not an area that I've worked in, but there is already quite a lot of work in both the use of AI for hardware design and the use of AI in verification of hardware designs, especially in writing test benches, but more broadly in verification of hardware design. And I think there is definitely scope for that. So I think perhaps one of the more tricky things is how to make the best use of a technology that is slightly opaque in terms of what's going on and understanding, the reliability of what's going on. What you definitely need is in the hardware design process is a reliable end-to-end process. Now, you can, I think, achieve that by having an unreliable design process that you can then verify reliably, or you can achieve that by having a reliable design process that you then use some unreliable bug-finding technology to improve your coverage, right? So both of these are possible. At the moment, this is where I see the direction moving.
And in terms of the more broader AI perspective, so for example, Geoffrey Hinton recently talked about the safety of AI, and he's quite concerned. Like if AI is been developing like this, at this speed, there will be a lot of safety concerns. Do you share the same concerns? Like, would you think like AI, would that be a threat for like humans or whatever?
It's a big question. Okay, so I think AI systems are tools. They're tools that aim to improve our productivity as humans. They aim to improve human labor productivity. They don't always succeed in doing so at the moment. Maybe they will one day, but that's what they are. They're tools. So I don't see AI in this sense as being any different to any other tool. Now, that doesn't mean it's not dangerous. There are many dangerous tools out there that we can use. If you bring a new productivity enhancing tool into a production process, then as an engineer, you need to ask a few questions. And if you don't understand the limits of what it's going to do, you don't understand exactly how it's going to behave in a given situation, even if it's, a power sander or a drill, it's a new tool. And if you don't completely understand how it's going to work in a given situation, then you either need to use it in a very enclosed, safety, secure environment and not have it making decisions autonomously that are going to cause problems, or you need to understand more deeply what the limits of the possible behavior are. Both are necessary, I think, at the moment. My concern is not with AI as a technology. It's a generic concern about tools. My concern is that the profit motive pushes innovation to happen more rapidly than might be safe to happen. And that's true whether it's innovation in the introduction of the weaving loom in the Industrial Revolution in the UK or in AI ML today. It pushes innovation to happen more rapidly than it would do if we took it from the perspective of what's best for humanity and we tried to understand it more carefully and approach it more carefully. The profit motive drives innovation, understandably, because what you want to do is you want to get a competitive advantage over your competing companies. It's that I think is the real danger to humankind rather than AI or ML as a tool.
Completely agree. So it reminds me of the autonomous cars, like autonomous driving technologies. And people, for example, the cars when coming out, people thinking like it's not safe in comparison to horses, cars, but then people get used to it, knows its limits. And I think, like you said, more importantly is to slow down a bit and think about each part of it, whether it's the usage of the tools or like how to using it or the limitations of it. Some of the autonomous driving technologies were the same. Like many companies has been driven by the profits and claiming the current autonomous driving technology will be layer 3 or layer 4 or even higher, but actually it's lacking of full tests or enough tests to cover the corner cases of the autonomous driving. But currently we see a slowdown of that area at least, and probably for the AI as well. Previously, you worked as the Associate Dean of the Faculty of Engineering at Imperial. So what do you think is the single most challenging part, like in terms of making this world-leading faculty to the next level? Is this money, talents, or whatever?
Everything. So my responsibility when I was Associate Dean of Engineering, my responsibility was academic workload. And going back to what I was just talking about, productivity, I think there's some core questions that come out when you start to think about how do we spend our time? We need to be able to spend our time in a way that we feel is personally fulfilling. That's the reason that most of us are in academia. It's the fact that we love the topics that we work with and we want to work in a personally fulfilling way. We need to work in a way that is productive rather than spending time on, things that we're not best placed to do, right? There might be, things that we can ask for support with or get support to do and so on. Ultimately, we at Imperial College exist to do research and teaching, right? That's what we're there for. And so how much time do we actually spend on these activities? Do we do them in the best possible way? How can we learn from each other? And I think ultimately, how can we as academics have control over our own working lives? I really feel that having control over your own working life is not only important for personal well-being, but it's important for productivity. Because if you feel that you've got control over your own life, then you're more likely to do great things, I think. And so really that was the perspective that I was coming at as Associate Dean. And I think we've made some improvements. Shifting the way people work is never going to be an instantaneous activity.
But in your views, how do you balance the cutting-edge research and the education of both undergraduate and postgraduate? Because as you mentioned, our time is very limited. You can't spending times on all of these things. You have to make choices. So, but from the senior management point of view, how did you balance those?
So for me personally, I've had various different times of my career where I've balanced them in different ways. And actually, this is one of the real benefits of academia in the UK, is that it is possible to have that. For example, there were periods of time where I had a research fellowship where I only taught a very small amount and focused my attention on pushing forward a particular research project. And then there have been periods of time where I've also been responsible for one of our undergraduate degree programs and really focused a lot of my attention on pushing forward our education system. At the moment, I'm in that mixed economy mode where I'm doing a bit of both. And I'm really enjoying doing a bit of both. I think the ability to work with really, it's about excitement, right? So the ability to work with young people who are coming in as undergraduate students, usually they're age 18 or 19, and they're super excited about technology and the way that's going and want to know everything that you can possibly share with them. There's nothing better than spending time with these young people. Equally, I'm very conscious that I work at the cutting edge of research and I'm trying to push forward the international agenda. My view is that I'm able to do that. I hope others would agree. I'm able to do that together with some really outstanding PhD students. And again, spending time with those PhD students is another area of my major activity. So apart from my administrative roles, I really try and partition my time between these two activities. It's even better if they can cross over. So for example, we had an undergraduate student do a summer internship with us last year. I asked one of my PhD students to mentor him through that process. And we ended up publishing a paper at the top international conference, FPGA, together recently. So I think it's wonderful if we can get the whole chain working together and that they're not in conflict. But ultimately, I also have to be quite rigid with my time. And I say, on Tuesdays, I'm doing this, and on Thursdays, I'm doing this.
And in my view, one of the main differences between engineering faculty and some theoretical research, like mathematics or physics, is like for engineering faculties, they can translate their research much easily to like industrial applications. Would that be a main focus of the Faculty of Engineering at Imperial at all?
I mean, it's a main focus of Imperial, actually. Imperial was set up to have real-world impact. It's even in the founding charter of Imperial to have real-world impact. So I think absolutely that's true. I mean, I'm not sure that I would say that engineering is necessarily more so like that than other departments or other faculties. We see a huge amount of real-world impact from our medical faculty. In mathematics, applied mathematicians can have day one impact. Most of the kind of results in MATLAB, for example, the toolboxes are coming out of the applied mathematics field. So I think it's true actually across the board. What I would say is sometimes young academics, feel that there's a pressure to be the best at everything from day one. And that means that they need to be the best teacher, they need to be the best researcher, and they need to be the ones putting this into practice, and they need to have a startup, and they need to do this. It just doesn't have to be like that. Firstly, you can do different things at different points in your career, as I have. Secondly, it's fine if someone emphasizes pure research without kind of really understanding or being too bothered about where the impact is going to come from, so long as someone else is talking to them and is really interested in where the impact is coming from. And I think one of the advantages of working in teams in an environment that supports a culture based on team working is that you can have that specialization so that what works for you is possible.
So speaking of young researchers, recently you take on a new role on the Early Career Research Institute. Mm-hmm. What's that? So what's the point of doing that?
Yeah, since October 2024, I've been director of the Early Career Researcher Institute at Imperial College. So that's a group. We have about 30 staff in the institute. And our role is to support early career researchers, which we define as anyone from those who are just starting out on their PhD journey all the way to early stage academic staff, to support early career researchers with whatever it is that we feel and they feel that they need in order to make a success of their career. And so that's divided into a few different areas. So firstly, we're working hard to attract the best quality early career researchers from around the world. Secondly, we're looking to develop the skills and the activities of those researchers who are already here. So of course, there'll be development at a technical level that will be dealt with in their home departments. But there'll be other development opportunities like, how do you do well at interviews? How do you apply for funding and things like that we exist to support people with? So there's attract them and develop them, empower them. Going back to what I said earlier, it's really important that people are empowered and feel that they have the ability to shape their own working life. And I think that's particularly challenging sometimes for early career researchers who feel that their PI or their supervisor sometimes is kind of godlike figure. And being able to advocate for them, I think, is really important. And then finally, more broad advocacy across the sector. So, for example, I was doing some work with the EPSRC, with the Engineering Physical Science Research Council in the UK, on the levels of stipend that we pay students to study and making sure that they are kept in line with really the requirements to study and work in London.
That sounds very helpful. I wish I had something like help like in my early career. As you actually mentioned, some of the big challenges, like people trying to do everything, especially when they are young, which is very sensible because they basically need those stuff to help them to be promoted to move to next level. But in addition to that, what do you think would be the big obstacles for like young or early career researchers when they're facing in their career path?
Yeah, I mean, I think a lot depends on the environment within which the early career researcher finds themselves. And it actually does vary considerably, even within Imperial College. There are some standard things that you see arising across the university sector, in the UK at least. I think pay levels for PhD students can be problematic in that often, especially in my field, you can actually go and earn more in industry. So there's I think, advocacy for improved quality pay for PhD students, I think is important. When people become postdocs, which is in the UK, almost a necessary step, not quite, but almost a necessary step before getting an academic post. Usually people are mainly worried about the short-term duration of their contract. So in the UK, most academic posts in science and technology, at least, not so much in other fields, are quite long-standing contracts or even open-ended permanent contracts like my own. Whereas most contracts that are for early career researchers doing research work as a postdoc are short-term. And that's often the thing that really gets in the way the most because they're often thinking what their next step is from the moment they start their current step, which distracts from the research, actually. Yeah. So I think these are kind of big system level issues that I can't change overnight, but I hope to work with our early career research community and the university senior management to advocate for at a national level.
So that is another question or problem, actually, for early career researchers is how to define them. So how do you define or measure a people or researcher, especially in their early career life? Because sometimes people pursue publications, pursue grant fundings, and people, because in this way it's quantified, people can measure you because you publish several papers on top conferences and you got that amount of money in your research. So in your view, what's the appropriate measure or ways to measure or determine if a people is okay or has potential to do good research work?
It's a really complicated question. So I think the first thing I would say, there's a book by Jerry Z. Muller called Tyranny of Metrics, well worth reading. And it essentially talks, in line with the similar comments I made earlier in the interview, talks about how once you measure something, it often ceases to become a useful thing to measure. And all the various kind of negative impacts that has had over time. That doesn't mean that we don't have to sometimes measure things. So a good example would be when someone's applying for a job, obviously you have to decide who you're going to offer the job to, because there's one job and there's multiple applicants, okay? So then I think the first question that you always have to ask is why? Why are we measuring? For what purpose? Because what comes out from that, answering that question, is what you should measure, or how you should measure it, or how you should evaluate it more precisely, because measure implies quantitative, and quantitative doesn't necessarily fit everything, right? So I think that's the starting point that I would have. So I think what I would say is there is no answer to the question of what's the best way of measuring an early career researcher, because it depends for what purpose. Why are you doing that? And if the answer is because I have this particular job that's available, then actually what you need to do is to look and see, well, what are the things that job requires? That job, not them as an early career researcher, but that job, and then set up a way of doing evaluation in a fair way that meets those criteria. So I'm generally against measuring people. I don't think that's a good approach. And what I would definitely say is, above anything else, is some of the worst practices that I've seen are around counting publications. And at least the UK, in its research evaluation framework, doesn't do that. So when we do a university sector evaluation of the research output of the university, and it is the university, or rather units of assessment, rather than individuals, we don't say how many papers. How many papers is a really bad question, always. Rather, we might ask people, can you please provide what you think are the most important 3 contributions that you've made over the last 4 years? And then we'll read them and see what we think about those contributions, right? That way, at least, whether you've published 3 outstanding things or 300 mediocre things, the 300 doesn't come into the picture.
And then let's move on to the very early stage of research, which is the PhD, right? And first of all, congratulations on receiving the President Award for Research Supervision Excellence. That's a very big award. And as your PhD student, I know your supervision style, but I'm very curious on your supervisors, because you got 2 supervisors.
That's right,
One's the Professor Winlock and one is Professor Peter Chang. I'm very curious on their impact on your early career. Do you remember any moments, like you still remember, like they impact you or change you quite a bit?
Absolutely. They're very different characters, Peter and Wayne, and very complementary in terms of the way that they operated as PhD supervisors. Peter was my primary PhD supervisor. And then in due course, he became my manager, he became head of department, and so on. So I've worked with him for a very, very long time. What has been consistent over that time, from an early PhD supervisor all the way through, is that he has led by inspiration. So what I mean by that is he's not said, oh, it's Monday, do this work today. What he's said is, I find this thing really interesting. What do you think? And that's made you think about it. And that's made you do stuff. or you've seen him working really hard on something and getting a really positive response from people. And you think, I could do that. Let me try and do that. And it's that leading by inspiration that I think has been throughout that process. And I've tried to copy that. Probably not as good as Peter, but I've tried to copy that. Then the other thing is that both Wayne and Peter have always, or were always, completely open to spending time with me. You know, if I wanted additional time, they would make time to spend with me. And I think having that openness, I think, hugely valuable. Wayne, at the time that I was doing my PhD, Wayne was like he was a relatively young lecturer, and he was very details oriented, which helped me a lot also with fine tuning the way that I was doing my writing. He was giving me LaTeX tips, all this kind of like very, very detailed level stuff. So they were able to work together in a way that I think was really valuable to me.
I also saved my previous paper, so with your detailed comments on it. I should admit at first when I the first very few papers, I can't read your comments because it's too much. But I do feel like that's when I get my writing skills improved, especially English writing skills, because in that sense, how should I express, how do you describe your ideas, how to formalize a good paper. But currently, a lot of students, as far as I know, a lot of Chinese students call their supervisor boss because they actually pay them salaries and they actually give them tasks. Mm-hmm. Do you think this is the right way to call their supervisor? Or in other questions, what do you think? Because I'm currently a supervisor as well. What's your view on supervisor itself anyway?
I think the word boss is loaded. It comes with certain emotional baggage. So it can mean different things to different people, actually. It's not necessarily bad, especially if it's kind of viewed in a somewhat jokey way. So I would kind of shy away from saying that boss is bad. It's not necessarily bad. I think actually whether you're a student or a member of technical staff in a laboratory, whether industrial or academic, the same story holds, actually. It doesn't really matter whether you're a student or not, which is your line manager, if you're a member of staff, or your supervisor, if you're a student, are they providing you opportunity for personal growth? And sometimes the best opportunities that are provided for personal growth are actually by saying, I really think you should do this task. And that's okay. There's nothing wrong with that, because if it's coming from the perspective that person needs to do this task because they're going to be a better engineer after having done this task, not a problem. If it's a question of, I have this thing that needs to be done, do it. I mean, I think all life has elements of that. It just needs to not be dominant in the time.
You're talking about helping students to grow, but what do you think is the one single most important capabilities for the PhD students to study or to grow during their PhD study?
Curiosity. So I think, again, I believe in the fundamental plasticity of the human mind, right? That these are not things that some people have at birth and some people don't. These are things that you can develop over time, right? But I think the one thing that you really need to develop early on, ideally before you start the PhD, is a natural curiosity. If you read a paper and you're not curious about why they did it the way they did it, if you read a paper and you're not curious about what they're not saying as well as what they're saying in that paper, then I think you've got some development work to do before you can make a full contribution to research.
Yeah, exactly. So how do you think will be the specific developments can be done to help them to get curiosity mindset?
Yeah. So one of the things that I often do with my own PhD students, and you may remember this, is that very early on, encourage them to read papers from some of the most recent conferences. And that's partly to understand what it is that people are talking about at the moment in the field. But partly it's also because these are things that I've seen presented or read the papers and so on. And so I'm kind of aware where I think the weak spots of this work and the strong spots of this work are. And I'm wanting to understand, is that what the students also going to pick up on or not? And I think it's through that discussion process that we build that level of curiosity. I think also it's really valuable to give students exposure to the process of reviewing other people's work as well, because it's in that process of reviewing and indeed in teaching that you really gain solidity in your own understanding of what's happening and look at things through a critical lens.
So we talk about the supervisor from the supervisor point of view. So in the PhD standing point, right? So when people applying for PhD, for sure they apply for several reasons. For example, like in China, I know many people, because they can't find a perfect job, they would like to do a PhD to extend their university times, or like they like the research you've been working on. But in your point of view, what's the first principle of PhD education?
Well, I think so. Doing it because you like the field, I think, is a good thing. Probably needs to be a bit more than that, right? I think, but without that key ingredient, if you don't like the field, definitely don't do a PhD, right? Because it's all about passion. And so I think, yes, liking the field, being interested in the field, but more importantly, wanting to advance the field. And for me, that's the key distinction, really, between what comes before a PhD, typically a master's degree, and the PhD, which is that up to a master's degree, you're likely to essentially be learning things that other people have discovered. And in a PhD, your goal is to discover things. Now, that will also involve learning things, there's no doubt about it, but that discovery element has to be there for the award of the PhD. And I think, for me, the feeling, not only I want to learn more stuff, if you just want to learn more stuff, do another master's degree. But if you want to actually contribute to that field, that's the point at which you should be thinking about doing a PhD.
So looking back to many PhD students you've been supervised, what's the single most, the moment make you the most proudest?
Actually, I think it's seeing, there are many different ways that things that make me proud, actually. Many different things that make me proud. And mostly it's seeing what has happened later in life with those former PhD students. So a good example is sitting here today, right? I mean, honestly, it is, right? I'm very proud of what you do, and I think it's fantastic to see. Another good example, one of my former PhD students led a group of people at Intel who were involved in various aspects of design. And I spent about a week embedded with them a couple of years ago, and seeing the fact that he had created this group from scratch, and that each person there had clearly been recruited for a particular goal, and that they had each their own expertise, and that he'd been able to cohere them together as a team, and that they were doing amazing stuff, I think was profoundly moving, actually. Success comes in many different guises. For some people, it will just be that they are happy, in life, and that they look back on their PhD studies with fondness. For others, it may be other things. Whatever it is, that I don't have a particular thing, but I think it's often not so much about, I absolutely celebrate when they have a paper accepted, right? Let's celebrate, no doubt. But it's less to me about those immediate successes. It's about 10 years, 15 years down the line. What are they doing, and how did the PhD journey impact on them?
Yeah, for sure. My PhD journey with you at Imperial is definitely a life-changing experience. Not only because of academic capabilities I've been learned, but that's definitely very valuable, but also some transferable skills I think only the PhD can teach you in this journey. But recently with the AI coming up, acquiring knowledge is becoming very easy, I would say. Some previously, like, we have to stay in the libraries and checking the material, checking the informations, reading the papers. And now AI can do everything, all that kind of stuff. We can summarize the papers, reading all that kind of stuff, tell you what's going on. So in that sense, would the AI change anything on PhD supervision or PhD journey learning?
I think AI tools are productivity enhancers, as we discussed earlier. I think that there are definite places where AI tools can and probably even should, even with today's level of technology, be used to improve PhD supervision and PhD journey. I'll give you some examples. I think the idea that getting a summary of existing work presented to you is the same thing as having the knowledge is not quite correct. Even if the summary is correct, and with today's technology, as I'm sure you know, that may or may not be true. But even if it is correct, it's equivalent to asking someone else to do the job, right, of summarizing. So whether it's an AI or another human, and you say, please, can you go and write a summary report of this? There is value in that because it might help you to absorb that information more quickly. But that's not the process of absorbing the information. So it's not the same job. Where I think AI tools are currently of a lot of value is in accelerating, again, it's a productivity tool, accelerating certain tasks. So, for example, I've used large language models to an extent for this topic. I have a colleague, Eric Kerrigan, who I collaborated with closely in my department, who uses them even more heavily than me. Where in the old days, a lot of the work that I do is around identifying, creatively creating a problem, and then thinking, what mathematical or algorithmic tools do I have at my ability to solve this problem? And then thinking, okay, so once I do that, how does that change the problem? That middle step of understanding what tools and mathematics exist to address this problem, I find LLMs to be a useful way of accelerating that process because they essentially replace either your limited internal knowledge of the tools that you already know and are available, or a number of kind of Google searches. They replace that with some queries which return some results which may provide you with some insights into things that you can then pursue as techniques. They're not going to solve them for you, at least not with today's technology, but they will give you jumping off points. So you say, I have this theorem I'm trying to prove, and this is the starting point, and this is the ending point, but I'm not quite sure, what techniques to use. And you'll get an answer. Sometimes that answer won't be useful, but sometimes the answer will be very useful because you have forgotten or you never knew of a particular theorem. And when you go away and kind of read about that, you think, oh yeah, I can apply that in this context. So it can actually make that process a lot faster.
Yes, it's like the tool theory you just mentioned. It's just the productivity tool, which can basically remember everything. But it's actually the human self needs to figure out what kind of information is actually needed and how to make full use of these AI tools to make his work or her work more productive.
Absolutely.
Let's go a bit higher than PhD studies, but in broader education system. In an ideal education system, how do you think should we balance the skill development, knowledge consumptions, and even more important or equally important, the culture, like the curiosity, soft skill development? How do you think?
It's an interesting question. So I don't know if we've spoken about this before, but been involved in school level education for a long time as well. So I was chair of the board of a primary school, an elementary school. And then I was a member of the board of a secondary school, and now I'm vice chair of Imperial College's new school that it's set up for 16 to 18-year-olds in North London. over this period of time that I've been involved with schools, that question that you just asked has been asked and answered in different ways by different people, often politicians, in different kind of settings. And often the answers are given are quite different. Usually the argument is made of, on the one hand, people say what you really need is skill development, because knowledge you can just look up. And then the kind of caricature of the other argument is that's not real learning. Real learning is knowing stuff. And the reality is neither of these are really true, but both are kind of true, right? It's, again, a dialectical relationship between these two things. You can't really start to solve any problem without knowing something. You need some foundational knowledge to be able to solve a problem. But the task of solving a problem is a skill. It's not something that, you look up, oh, this is what this problem looks like, and therefore it's like a textbook. You just copy this thing and plug in the numbers in the right places. So definitely you need the knowledge as a prerequisite for the skills. But by then working through that, you gain more knowledge. And in the same way that, if you read mathematics, in the same way that if you only read the theorem statement, but you don't read the proof, you don't really understand what's going on. In the same way, you need that skills to develop your knowledge. So I think it's more of a kind of virtuous cycle between knowledge and skills. So I wouldn't kind of come down on either of these two things. What I would say is that in England, the curriculum that was introduced some years ago into the schools shifted things too far towards knowledge, in my opinion, and too far away from skills. But I think we need to find the appropriate mix.
That's very interesting, because I've read a book about think fast and slow. Mm-hmm. It involves two systems, like system 1 and system 2. Mm-hmm. System 1 is just a purely intrinsic, like 1 + 1 = 2. Mm-hmm. And second, system 2 is basically when you need to use your mind and brains to come up with very complex stuff. Mm-hmm. My view on learning and skill, like you mentioned, you can't master any skill without knowledge. Mm-hmm. So you basically need to translate as much stuff from system 2 as to system 1, make it intrinsic, make it your internal knowledge. Mm-hmm. And then you got more space to learn complex stuff and use the knowledge in your system 1 to make it your system 2 more efficient and things. But that's for sure that's how I teach my undergraduate students, because many people are just saying you got AI, we don't need any knowledge now. We can just look up and ask AI the correct answer. But in that case, you can't really making meaningful progress with that.
Well, firstly, you don't know what to ask. And secondly, you don't know how to interpret the answer you're given.
Exactly.
Yeah.
Exactly. Right. So let's go to some kind of open questions, right? So back to technology, because people are talking about the end of Moore's law for ages.
Yes.
But, although it's still progressing, yes. But it's progressing slowly. But are you optimistic or pessimistic about the future of computing specifically? For example, with the explosion of AI, is the computing power going to be converged to GPUs or specific computing technology? Or will there be new technologies coming out to facilitate another wave of computing?
I'm not an expert on Moore's law at the fabrication level. As you say, I've observed Moore's law being killed off multiple times during my career, and it's always been resurrected. But ultimately, if there's one thing I know about exponentials, is that they don't last forever. There is a kind of a limit here, no doubt about it. So I think the first thing I would say is that's actually great news. That's fantastic news for humans. It's fantastic news for creativity. You could work really hard on a really interesting new way of doing things that makes things more efficient, lower power, lower area. And maybe it takes you a year to devise this thing. In the meantime, maybe we've moved to a new technology node, and the old way of doing things beats the way that you had before. So all you needed to do is to wait. I mean, I'm being a bit facetious here because, of course, the people working in the fabrication plants were working really hard to make Moore's law happen. It's not a natural law, right? But as a designer, you could say all you need to do is wait. Not true anymore, right? If indeed the exponential growth comes to an end. And so any real design advantage translates into actual advantage for the end product. And so that's a huge advantage to us. And so for the field, of creative designers, I think it's a great thing. Absolutely wonderful. We won't just rely on old things being scaled anymore. So I think that's the first thing to say. The other thing is, again, I'm not someone who works in kind of non-CMOS based design, but there are many different other ways of doing compute. My colleague Steve Ferber used to always point out how the efficiency gap between the human brain and CMOS-based computation. So I think there's a huge gap there to close, even over the human brain, but let alone over kind of lower bounds on computation that come from physics, right? And so I think there's a lot of work to do from the physics level all the way up to try to address those. So I'm hugely optimistic for the future.
Right, if there's lots of opportunities, but for young designers or architects, what kind of skills do they need? Like, because we talk about hardware design, we talk about AIs, we talk about software. Do they have to be both proficiency in hardware and software and others?
I mean, it depends the area in which you work. Nobody can be hugely skilled in everything. But if there's one thing that I would take away from my entire career, actually from undergraduate onwards, it's that some of the most interesting and some of the most exciting things to work on span two traditional topics. So whether that's hardware and software, whether that is mathematics and library IP design, things that are usually done in different boxes by different people. If you can look to industry and say, you can identify many places where someone does this task and then they hand it to someone else to do some other task. Anywhere where you've got that thing happening, where someone has this skill set and they hand it to someone else, usually there's a really exciting piece of work to be done at the boundary between those two. And so nobody can learn everything. Nobody can be an expert in everything. But I do think boundaries between existing disciplines are always rich for research opportunities.
My last question. So for people watching these videos, many of them is actually young students or people who would like to be involved in technology, computer science or electronic engineering area. What advice do you have for these young people?
I mean, be curious. Be curious. Talk about your work. Communicate what you do. I think one thing we haven't really touched on in the interview so far is that research is not just about discovery of things, about communication of those things, understanding what other people do and telling people what you do. Being able to communicate clearly and being curious, I think you'll go far.